এত কিছুর পরেও কিন্তু আজকে উনি এখানে এসেছেন। উনি বলেছেন যে ওনার কাছে একটা চ্যালেঞ্জিং, কারণ কি আমাদের যারা আন্ডার গ্রাজুয়েট স্টুডেন্টস রয়েছে তাদের সাথে উনি ইন্টারাক্ট করবেন, যেটা কিন্তু উনি ডেলি বেসিসে করছেন এমনটা নয়, কিন্তু এখানটা ওনার কাছে একটা খুব বড় একটা চ্যালেঞ্জের জায়গা, ভালো লাগার জায়গা, এক্সাইটমেন্টের জায়গা। সুতরাং এক্সাইটেড আছেন আমরাও। আর কিছু কিছু বিষয় থাকে যেগুলো মনে হয় তার সাবজেক্টের গণ্ডির বাইরে গিয়ে সকলের ভালো লাগে। যেমন একটা খুব সুন্দর ফুল, বটানির স্টুডেন্ট না হলেও কিন্তু সেটা ভালো লাগা যায়। একটা খুব সুন্দর পাখি, তার নাম জানি না, তার জন্য জুলজি পড়ার দরকার পড়ে না। ঠিক সেরকম জিওলজির মধ্যে অনেক টপিক আছে, বিশেষ করে এরকম যদি টপিক হয় যেখানে একদম দ্যুতিময় ডায়মন্ড, তাহলে মনে হয় তার একটা আলাদাই আকর্ষণ রয়েছে, সেটা আমি জিওলজির বই বা নাম। আর ওখানে একটা লাইন আছে আনটোল্ড স্টোরিজ। এরকম অনেক আনটোল্ড স্টোরিজ কিন্তু জিওলজি স্টুডেন্ট হিসাবে আমাদের কাছেও এখন খোলা হয়নি, অর্থাৎ আমরা নিজেরাও জানি না। খানিকটা জানবো, কিছুটা চেনা, কিছুটা অচেনা, অনেকটা অচেনা বরং বলা যায়, কিছুটা না বলে। তো সেই সমস্ত কিছু অপেক্ষা করছে আমাদের কাছে। প্রথমে স্বাগত জানাই আমাদের মধ্যে উপস্থিত হয়েছেন ডক্টর মাইনাক মুখার্জি, এবং আমাদের মধ্যে রয়েছেন সকল অনুষ্ঠানে বা যে কোনো রকম উদ্যোগে যাতে আমরা সঙ্গে পাই আমাদের ওয়াইসি ম্যাডাম ডক্টর শিবনদীপ ভট্টাচার্য। দুজনকেই স্বাগত জানিয়ে আজকে এই পথ চলা শুরু হোক। আর যিনি আমাদের সঙ্গে সবসময় থাকেন, শুধুমাত্র ছবিতে নয়, আমাদের চিন্তায় মননে সবসময়, তিনি হচ্ছেন ভগিনী নিবেদিতা। তো তাকে প্রথমে শ্রদ্ধা জ্ঞাপন করে আজকের পথ চলা শুরু হোক। আমি অনুরোধ জানাই আমাদের মাননীয় অতিথি মহাশয়কে এবং আমাদের ওয়াইসি ম্যাডামকে। স্টুডেন্টরা রিকোয়েস্ট করবো সিসিএস মহাশয় ভারত দিকে ট্রেন আসতে। আমাদের এবং যাদের জন্য আয়োজন সেই ছাত্রীদেরকে অনুরোধ করবো এগিয়ে এসে তাদের সকলের তরফ থেকে পুষ্প দেওয়ার জন্য। আমাদের মধ্যে উপস্থিত হয়েছেন, আমাদেরকে এতটা সময় দেবেন, এত কিছু আমাদের সঙ্গে ইন্টারাক্ট করবেন, তার জন্য আমরা তো এমনিতেই আপ্লুত। তো আমরা ভীষণভাবে চাইবার ছোট্ট স্মারক আপনার হাতে তুলে দিতে, এটা আমাদের আনন্দ এবং সেটা আমাদের ওয়াইসি ম্যাডামের কাছে। ওই যে শুরুতে বলেছিলাম কিছু উপহার দেবে। কদম ফুলটা আছে বিশেষ আকর্ষণ। এরপর আজকের এই দিনটি, এবং আমি তো আমার এক্সাইটমেন্টের কথা বলছি, বাকিদের এক্সাইটমেন্ট চোখে মুখে প্রকাশ পাচ্ছে, কিন্তু এবার ওয়াইসি ম্যাডামকে রিকোয়েস্ট করবো তিনি আমাদেরকে কিছু বলবেন।
Hello, our distinguished guest, Professor Mainak Mookherjee, all my teaching and non-teaching colleagues, and my dear students, I extend my heartiest welcome to all of you. We have assembled today for the 4th Annual Sister Nibedita Memorial Lecture to commemorate the 10th Foundation Day of our college. Yes, we are celebrating our 10th birthday. And it is indeed a very proud moment for us to have among us Professor Mookherjee, who is a scientist and professor of international literature. For the first time in this institution, an international level lecture is being organized. I think everybody will agree that nothing could celebration of 10th Foundation Day. I must thank Dr. Nibedita for making this happen. Earlier on this occasion, we have listened to lectures on space science, on journey of an eminent musician, on archival values from an eminent historian. Today we are going to listen to untold stories of diamonds before they adorn us in our jewelries. Diamonds are said to be the girl's best friend. Now, let us listen to their untold stories. Thank you.
যার নামে নামাঙ্কিত আমাদের কলেজ, তারই স্মরণে এই মেমোরিয়াল দিচ্ছে, যেটা চতুর্থ বর্ষে সে আছে পরিত। অলরেডি ম্যামও বলেছেন এবং সেই কথা আরেকবার সূত্র ধরে বলি, ওনার সাথে আমাদের পরিচয় কিন্তু খুব অল্প সময় সামনাসামনি। পরিচয় যদি বলি তাহলে কাজের সূত্রে দূর থেকে হয়তো অনেক আগে, কিন্তু সামনাসামনি পরিচয় বড় বেশি দিনের নয়। তার মাধ্যম হচ্ছে যাদবপুর ইউনিভার্সিটি এবং নিবেদিতাদের থ্রু দিয়ে আমরা প্রথমবার ওনার সাথে যোগাযোগ স্থাপন করতে পেরেছি। তো পরিচয় পর্ব আস্তে আস্তে যদিও চলবে, যদিও আমরা সবাই বিশ্বাস করি পরিচয় পর্ব ইন্টারাকশনের থ্রু দিয়ে হয়, একতরফা থেকে নয়। তবে যেটুকু পরিচয় আমরা পড়াতে পারবো, যতটুকু বলে আমাদের ভালো লাগবে, সেই অপরচুনিটিটা তো আমরা ছাড়বো না। আমরা তো খুব লোক অন্তত এই ব্যাপারে, তো সেই জন্য সেই দায়িত্বটা আমি নিবেদিতাকে দেবো। নিবেদিতাকে আরেকটু পরিচয় করিয়ে দিই, তারপর আমরা ডায়মন্ডকে যেমন চিনব থ্রু দ্য আনটোল্ড স্টোরিজ, ঠিক সেরকম ভাবে ওনার সাথে ইন্টারাক্ট করতে করতে আমরা ওনাকেও চিনব অ্যাজ আ প্রফেসর। অলরেডি কিন্তু আমি শুনেছি উনি যখন বলেন সবাই মন্ত্রমুগ্ধ হয়ে শুনুন, সে জিওলজি কি কোন ডিপার্টমেন্ট কিছু এসে যায় না। সুতরাং আমরা সেই মোমেন্টের দিকে এগিয়ে যাবো।
ওরা এত সুন্দর করে বলে দিয়েছে, তারপরে আমি তো অফিসিয়ালি কয়েকটা কথা বলবো যেগুলো না বললেই নয়। Today we are extremely honored to have Professor Mainak Mookherjee of Florida State University among us as our guest speaker of the 4th Annual Memorial Lecture of this institution. I would like to introduce Professor Mookherjee with the audience. Dr. Mainak Mookherjee, distinguished professor of geology, did his BSc from Jadavpur University in 1997, MSc from IIT Bombay in 1999, and PhD from University of Cambridge in 2004. He worked as postdoctorate fellow in University of Michigan, Yale University, as visiting researcher at Bayerischer Institute, Germany, and as research scientist at Cornell University before he joined to Florida State University as a faculty in the year 2015. Professor Mookherjee is considered as an expert in the field of mineralogy and crystallography, advanced topics in geochemistry, geophysics, and physical geology. He received multiple grants for collaborative research from National Science Foundation. He attained prestigious Fulbright Nehru Academic and Professional Excellence Fellowship. He is the recipient of Raghav Paul Junior Faculty Enhancement Award in 2017 and National Science Foundation's Career Award in 2018. He was elected as the Fellow of Mineralogical Society of America in 2023 and Global Visitor Fellow Earth and Planets Laboratory, Carnegie Institute of Science, Washington, D.C. in 2024. Professor Mookherjee has a phenomenal publication of more than 70 articles in different peer-reviewed high-impact journals, apart from book chapters, numerous conference proceedings, and others. He has delivered a lot of invited lectures in different academic institutions of USA, UK, Europe, and India. He has been the committee member of the MSc Lecture Program and Neurological Society of America. He belongs to the editorial board of Scientific Reports and become Neurologist Frontiers in Art Sciences and Art and Planetary Science Lectures. He has served as reviewer of a number of highly reputed international journals of art sciences. So we are genuinely feel privileged to have Professor Mookherjee among us today in this institute. institution. Now we cordially and respectfully invite him to deliver his lecture. Today he will talk on, as we can see, diamonds, origin and untold stories. So Professor Mookherjee, please come. That's it.
That's it? Oh, okay, thanks. So before we begin the talk, I want to really thank all of you for showing up here and Dr. Acharya for welcoming me and Dr. Chakraborty for facilitating this entire presentation. I'm excited and equally nervous to present it to an audience which is diverse in its composition, age group, career stage, and background. So I've never done this on the lecture, so this will be a first. And if you have questions, do not hesitate to stop me while I'm giving this presentation. Many of it will be accessible, mostly storytelling. The Untold Stories are essentially, should be very straightforward, but then there will be a part which will be a little bit into science, of colors, patterns. Eventually I will talk a little bit about environmental impact and so on and so forth. Yeah, that's all for today's program that I have in mind. apologize for all the delay and technical glitches. But finally, we have a working presentation. I don't know whether the slides will show some blanks or the figure or not, but let's hope that will work out. So, as you can see, today's talk, my topic is diamonds. That's something that everybody should be familiar with. It's a gemstone variety. In reality, diamond is nothing but carbon. I'll be talking about that. This is a famous diamond. It has a color. It's blue in color. Typically, diamonds are colorless. We'll be talking about what creates color in diamonds. This diamond is a special one. More than 200 million people have seen this since 1950s. It is hosted in Smithsonian Museum in Washington, D.C. And its origin, very likely, is from India. And when I was told to give a popular lecture, I was thinking about, I've never done that. I was told also there will be students who do not have science background. So I was in a dilemma. I typically give general lectures to science audiences, which have a common point where I can relate fundamental science like physics and chemistry with geosciences. So this is a special one, which is inspired by a talk that I myself a couple of years ago in Geological Society of America's past president of the Geological Society of America gave this talk. His name was Professor Jeffrey Post. He was a curator in this Smithsonian lab, and he presented a wonderful story of this diamond, which is called the Hope Diamond. So I'll be walking you through the history of that, mostly the human history, which is more or less really accessible, the story of the journey of the diamond and also the human story associated with it. And after that, I will gradually get into the details of what diamond is, how you have colors and everything. This is the same diamond from the shape you can tell. It's essentially lit up by ultraviolet radiation and it glows red. And I'll talk about that and how that can be used as a fingerprint for decoding diamonds. And this is essentially showing you a picture of a big hole, which is essentially the kind of rock types when it erupts, carries the diamonds with them. It's extensively mined. This is from South Africa, and now the mining has stopped and it's essentially filled by water and lake. This is the big hole from Kimberley, from which the name of the rock diamonds came alive. Am I talking too fast? Please, by all means, interrupt and ask questions. Do not hesitate.
Next. Hey.
How does this work? Technological challenges. Okay, wonderful. As I was mentioning, this is the Smithsonian Museum. This is where this is located. This is the Hope Diamond. And more than 2 million people have actually seen this. This is taken from a popular article written by Jeffrey Post and his French counterpart, Professor Farges. He was also a curator and professor in Natural History Museum in Paris. So the story goes that this diamond was actually found in southern part of India in a place called Kollu Mines. And there was a French traveler in the 17th century named Jean-Baptiste Travanier. He essentially went and visited and came when the context of India, he came and visited India several times. And he was a traveler, and he has a book in French, which was translated by the geologist resident in India. He was a geologist in the Geological Survey of India, and he translated his travel memoirs to find out the locations of the mines. Some artist rendition of this French merchant traveler, Jean-Baptiste Travanier, and he himself over here, seen in the context of an Indian setting, very likely close to a place called Golconda, which is very close to Hyderabad, present-day Hyderabad, in the state of Telangana. Okay, he most likely bought this diamond from this Golconda mines and defined it as a beautiful violet diamond. This shows the map that that's the kingdom of Golconda. This is a very old map. This river is Krishna River, and very likely there are some Kimberlites. I'll show that towards the end. Kimberlite is a kind of rock in which diamonds are hosted. They essentially erupt very fast, and there are several southern Indian Kimberlites. And then it goes through erosion. That means essentially the rock decays, and diamonds are essentially washed along the rivers, and then they get deposited in some sort of clay pit mines or alluvium plains, and then it was mined to extract diamonds. And many important diamonds were actually found in this region, including Kohinoor, which is of course a very contentious diamond, but I chose to talk about Hope diamond, which has a nice blue color. So the diamond mining at Kollur mines was very crude, as one could imagine. And from at least when I grew up, I used to watch Satyajit Ray's movie, Hero Raja Deshe, and so on. And the mining conditions when they were great. It was of course a political satire. There was comic elements which children could enjoy, but at the backdrop there was this kind of aggressive, production-oriented mine and diamond extraction. The story was not very different over here. The miners slept in huts covered with straw and were often given food instead of money. The pit wall had no timber support and caved in after heavy rain, somewhat like today, killing dozens of men at a time. Women and children, shown over here, worked above the ground. This is essentially washing the rock particles to get the diamonds. That's what essentially is depicted over here. This is from the Diamond Washing at Golconda, a book by John Harris, which is now incorporated in the historic mining in India. If you go to the Geological Survey of India's website, you'll be able to get this particular document on this figures as well. This is showing the mining condition inside the mine. This is the outside surface, and essentially you're going down in the pit. It gets, you just get filled with water because the water level was very high and so on. So it was a very difficult condition to mine diamonds. Okay. So Jean-Baptiste Tavernier bought the diamond. Don't know what the price is, that's not reported. And then he took it back to France. And the ruling king at that time was Louis King XIV. And he bought the diamond along with many other diamonds. I'll show that in a moment. This is the figure of King Louis XIV. And this became the crown jewel of the French kingdom. The diamond that originated in Kollur mines in India. These are all the diamonds that these are all the diamonds that that Jean-Baptiste had. I don't find that. This doesn't. The pointer doesn't like me somehow. It doesn't work. Gentleman does it wonderfully. Anyway, this is the French blue diamond shown over here in the Victoria River Station. It's a very big diamond. A carat is roughly 0.2 gram of weight, and it's a very, very big diamond that we bought. And then there are other additional diamonds that was also sold to Louis XIV. Thanks. So, why the kingdoms would have jet covers and so on? Imagine the history. If there are students of science and physics, you might have come across development in optics. One fundamental thing is Snell's law. Essentially, it talks about the refraction of light. While this diamonds are bought, there are lots of development happening in physics as well. So the jet cutters have that knowledge, and I'll try and show you why diamonds are so special, how you can essentially enhance brilliance and so on, what kind of cuts are important. Anyway, this is a photoreal of a diamond, what it would have looked like during the kingdom. This is blue color, and it was essentially set in a diamond, in gold, so that it will essentially have this radiating pattern of the sun. The king was a sun king, so it essentially reflected his ideologues and so on. And then sometimes it will be placed in this sort of emblem, which will be during ceremonial occasions on the roads. So this is a computer photorealistic simulation in the French blue diamond, when set in gold as described in 1691 inventory of the French crown jewels. And this is the color rendering of King Louis XV's emblem of the Order of the Golden Fleece. I'll show you how it looked like when it was worn by the next king, which was King Louis XV. So this is King Louis XV. He also made some adjustment, some further cuttings to the diamonds so to have a brilliance reflected. This is the same emblem over here, the diamond is shown over here. This is the French blue, it's a large diamond. And this is where the king is wearing his regalia of diamond. And then it was passed on to King Louis XVI. There was, during King Louis XVI, there was, of course, uprising in France. French Revolution was right corner, and Queen was Queen Mary Antoinette, and there was a lot of happiness in the normal public. The French Revolution happened, and King Louis XVI and Mary Antoinette wanted to flee. They were caught, they were brought back, trials happened, and then they were beheaded in guillotine. And after they were beheaded, the diamonds were essentially taken by the government. It was placed in some sort of a safe house, but during French Revolution there was some looting, and the diamond was stolen. And this French blue diamond episode ends. This is a triangular diamond which originates from Kollur, but then it kind of got lost. Several years later, in 1812, after French Revolution and so on, in 1812, another large piece of blue diamond was found in London, and it was referred to as London blue. And somehow there's strong evidence that the French diamond, which had a triangular shape, now changed its shape, and it was essentially adorned by King George White. This diamond was then sold by King's after King's death. There were lots of debt, and so the diamond was sold. And it ultimately went to a person, a banker named Hope. That's how the name Hope diamond comes in. And then Hope passed away, and then there were lots of litigations and battles who would have all his properties, and eventually it went to one of his nephew, and then the nephew also got bankrupt, and the diamond was sold to a person in New York. Then the person in New York had some cash issues, wanted to sell it. The Frankers and Sons sold it to a person in France named Salih Nabi. Then it eventually came to diamond merchants or diamond jewelry makers. Pierre Cartier, which was a very famous diamond makers and the jewelry makers and so on. Pierre Cartier then eventually enticed one of the aristocrats in Washington, D.C., named Evelyn Walsh McLean. She was told a very interesting story about the origin of the diamond, that it was made by a French traveler who had a very tragic death. Then it went to the French kingdom, which then it was adorned by Mary Antoinette. She was guillotinized, and then it went to King George, fell into poverty. So it has this elements of curse in the diamond, essentially getting built up. So she was very enticed, but when the diamond was shown to her, it didn't have the nice kind of setting, she didn't quite like it. Eventually, after a year, Cartier put the diamond in a nice setting, and the diamond was sold with the condition that if any curse falls on her, the diamond would be returned and the money would be given back to her if it happens within 6 months or so. Nothing happened until 10 years, and after that her son had an accident and passed away, and then eventually bad luck fell on her. So this diamond came to known as very cursed diamond. So two different diamonds. Are they connected? French blue was lost and stolen. Then this is the Hope diamond, which was essentially originating from London. Had also a very blue color, but not known because the shape was different. So it was kind of a mystery whether the two diamonds are same and whether they're related. Much later, this is, by the way, when Cartier sold, that's the first evidence of the price of the diamond. This was sold in 1911. This is essentially the cash receipt. This is from the Forbes magazine, and the price for the diamond exchanged at that time was around $181,000, which would be millions of dollars now, and of course, given its historical value, it's priceless. And that's again Evelyn wearing the diamond over here. Eventually, when she passed away, the diamond was given to Henry Winston, which is a company that held the diamond, made shows across US, which are shown over here, the dark blue color. And this was essentially a cast. When the jewelers used to cut the diamonds, they used to make a lead cast. And this lead cast was lost, but somehow it was found in the Natural History Museum of Paris by Professor Cortez, and he brought it to US, and there were lots of computer simulations that were done whether this particular Hope diamond would fit in within this diamond, and the next figure shows that. This is the outline is essentially the French blue, and the Hope diamond fits nicely, but there are two blues, B and C, and the Hope diamond was recut. Of course, it lost weight and changed carats, but now there's at least a little bit more quantitative evidence that the Hope diamond and the French blue are one and the same. Still cannot be proved because there are missing links, but this is the best that this gemological science has provided us so far. The other aspect, during the beginning of the talk, I heard diamonds are a girl's best friend. Yes, to some extent that's a tagline that was created, but let me tell you a little bit about the story, how it came about, why suddenly it became girl's best friend and not man's best friend or whatever. The idea is the gem industry, production of gem is extremely small. The yearly consumption of gem, which includes diamonds, rubies, sapphire, all kinds of gems, is around. Can you hear me? Counting. Just doesn't want me to give the talk, I think. So it's around 10,000 kilogram of gems are produced, but the price is enormous. It's $1 billion industry, and it's $5 billion industry in US dollar of raw material. And raw material means when you get the diamond from the rocks. After that, when you polish it, the values go up tenfold and so on. This is a 2000 estimate. The current estimates are much higher. I'm taking it from a book. These are prices from 2000s. Prices have gone up significantly. I know it because I use diamonds for my research. I use it as an optical window. Diamonds are very hard, so I use it to compress material to go to high pressure to simulate conditions within the earth. It's a very expensive gem. Okay? But this diamond is forever is essentially a creation of a company. And let me walk you through what this is. Initially, the diamond trade was, or the diamond and interest in diamond was very much confined in India. Most of the great diamonds came from India. Then the Britishers discovered diamonds in other parts of the world. One was Brazil, and the other one was South Africa. And it was soon found that there's a lot of diamonds in these steel light pipes, much more than what India provided. India provided very good quality diamonds. So it became a problem because the price of diamonds will go down because there's already a market in Europe. The diamonds are extremely expensive, rare gems, but now suddenly you have lots of diamonds in South Africa and in South America. So the company, De Beers, essentially consolidated all the diamonds to create a demand for the diamond, so that they ultimately control the entire diamond output, so that you won't have access to it, so there will be a lot of demand. The next thing was to essentially make sure that there's a buyer for the diamond. And the buyers for the diamond were primarily the US, because there was this kind of the De Beers essentially hired a company named NW Hires, and they hired an ad writer, and I'll show you about her in a moment. They created this tagline, "Diamond is forever." The idea was that if you love your beloved, then the best gift that you can give is a diamond. There's no compromise. And that became a culture, and it became a non-negotiable gift during courtship and engagements and so on. So this is essentially from Scientific American, and I wanted to show you the South African diamond. So this is the writer, the ad content writer. Her name is Frances Garrity. She almost wrote all the ads for the next 25 years. It's a creation. that essentially maintained the demand for the diamond and so on. And of course there were changes. Earlier, the diamond cutting and polishing was primarily concentrated in Belgium, in Antwerp. Many Jewish jewelry polishers were essentially interested in large diamonds, and the customer base was mostly wealthy Western world customers. Eventually, Indian Gujarati people went to Antwerp, learned the trade, and they found that there was no interest in the small diamonds, which are often referred to as diamond plus. So they focused on the diamond plus, which is smaller diamond, and as the middle class of America became richer and they wanted to get a piece of diamond as well, and of course wanted to save resources by essentially going for smaller diamond, then since 1970s it became a kind of a trade in India, and Surat is now a wonderful place for diamond merchants who are essentially polishing the diamond. That means they buy the raw product, and then from there they essentially polish it, and that's how India got into the diamond polishing business in the modern era from 1970s. Of course, De Beers is no longer holding the monopoly of diamonds and controlling it. It's often Russia, so the Ukraine and Russia war has affected that in some ways, and the diamond trade and the workers who are essentially polishing it are also getting affected. But then towards the end, I will tell you what are the alternatives to that. So this is essentially showing you a lady essentially getting a diamond. Prices are mentioned over here, humongous price, and this is from 1911 or that era. Essentially, that's how the diamonds, whatever phrase came about. I'll take a pause over here. This was non-science part story that probably have bored you a lot. But if you have any questions, I'll take that question and then essentially go into the physics and chemistry of the diamond. If you have any questions, I'll take that. No questions. Either you understood everything and ready for an exam, or you've given up. Either of those. So these are different gems. Their chemistry is different, and their finger typing, since the chemistry is different, their bonding environment is different. So there are methods like Raman spectroscopy or X-ray diffraction that can tell you what material they are. Yes, they may have color. Color is a phenomenon that is dictated by. Color is a phenomenon that is dictated by how electrons can absorb energy, light energy, and essentially whatever is absorbed, you see the complementary color. But that can be created, the same blue color can be created by a variety of ways. So just by looking at color, yes, it will look similar, but then of course there are devices which can tell you how different they are. Those are essentially what the mineral properties are. So thank you for the question. So that was more of human story now. I hope there are some science students in the room, and they will probably have some similarity, some familiarity with what I'm going to talk about, mostly physics and chemistry, which you may have encountered during your high school days. And if you haven't, then I'll try and make it simple, ask questions, and I'll try and answer. So this is essentially a natural diamond found in the rock. This comes from a magazine named Elements, a magazine in 2005 dedicated to the origin of diamond, and that's essentially where most of this comes from. This is a periodic table. Most of you are familiar with it. At some point in time you have seen it. This is where carbon sits, and it's essentially carbon. And I'll also talk about a little bit of boron and nitrogen and how they can impart color in diamond in ways. Carbon has 6 electrons. Electrons are held close to the nucleus, which is essentially positively charged. There are neutrons, protons. Neutrons are neutrally charged, protons are positive, and then it's surrounded by electrons. In a classical way, you can see this is the nucleus, and we have 2 electrons, and there are 4 valence electrons in a diamond. And this is a very classical way of presenting it, how carbon forms a covalent bond and then sharing of electrons with other carbon atoms. If you go a little bit more than this particular classical way of looking at shells as circular orbits, then you know that there will be shapes associated with this kind of molecular orbitals. The first one is called the s orbitals, then the next one is called the p orbitals, which has a double shape. And carbon, given that it has 4 electrons, the first 2 electrons goes in the s shell, and then the next 2 electrons goes to the p shell. And so what happens is that you have 2 electrons over here and 2 electrons over here in the ground state, shown in this particular configuration. Then it tries to make it a symmetric distribution of electrons to form the bonds. So this is a perturbed or promoted state in which one of the electrons from the s goes to one of the p electrons. There are 3 in the p and 1 in the s electrons, 4 electrons each. But then it's essentially the electron is occupying one lobe and the other lobe is empty. Electrons at the top lobe, of course, it has a wave character. But then eventually, to make it more symmetric, it becomes a tetrahedral kind of a configuration. So this is what the diamond structure is. It's a very covalently bonded star that gives it strength very hard and also makes it colorless. So whatever I showed in the other figure, it's essentially the same representation. Instead of black and white, it's a colored figure in which all these purple atoms are carbon atoms. They are forming this kind of tetrahedral configuration, which comes from the sp3 hybridization. That 3 p orbitals and 1 s orbitals combines to form a tetrahedral coordination. And then, how do I get to the shape? Well, this is the crystal form. If you repeat this tetrahedral shape forever, then you essentially get to this particular shape by this kind of, this is essentially a representation of the shape. And then, just the outline of the shape is shown over here in the red. It represents this diamond over here. These are the faces of the diamond. It's very hard, it doesn't have much brilliance, but that's how nature provides you with a raw diamond. What jewelers do is take a shape like this, and then they cut open the first part, the pyramid is removed, then you have a table at the top, then they essentially polish it to make it more circular, and then they add different facets. This is how a gem variety of diamond is created. And there's a reason why they do so. They use Snell's law and total internal reflection to essentially enhance the brilliance of diamond. Imagine looking at a colorless object like glass. If you shine a light will essentially go through the glass, and you will not be able to see the glass that much. But if you have a mirror, it will reflect the light back. So essentially by making all these facets, you're trying to trap the light and essentially concentrate the light back to your eye. That enhances the brilliance, and that's why the shapes are done. If they are not cut, not polished, you will not have good brilliance. So the grade of the diamond is of course the carat, clarity. If there are any defects, you should not have any defects, which are essentially great for geologists, but not for the gem industry. And then the other thing is the cut. The cut is extremely crucial, and the small diamond, difficult is the cut, and that's where I think India comes in, and the Gujarat and Surat essentially masters that particular problem. Okay? So this is essentially showing you a ray getting in, and each of these rays, although it is transparent, it's essentially reflected back, because only the reflection of diamond is a very high refractivity, and faces the full ray in the hospital light, and that essentially enhances its brilliance. Okay? Now, okay, that is brilliance. It's made of carbon, it's transparent, it's colorless, it does not have color. That means it essentially has a conduction band, a valence band. Electrons do not absorb the light energy and essentially jump around with the conduction band. How do you then get the color? Well, from color, let's walk through this particular electromagnetic spectrum. It goes from all the way, very long wavelength electric waves, which has very, very low energy. It's given in electron volt. That's the energy that an electron gets accelerated through a potential of 1 volt. So it's a long electric waves over here, then you have radio waves, then you have microwave, something we have heard, infrared, which essentially creates heat. Then comes a visible range, which is essentially what our eyes are sensitive to. This is the normal visible light. It's a very small window, and after that we have ultraviolet rays. You may have heard that if you go out and there are UV radiation, you need to protect your skin. And the reason is as the wavelength of the electromagnetic radiation becomes shorter and shorter, the energy becomes larger and larger, which has the ability to dislodge electrons. That means it will become cancerous if your cells are dislodging electrons, and obviously if you're exposing yourself to ultraviolet, then that will be a danger, because after that you have X-rays, and then if you have further higher energy radiations and short wavelength, you have gamma rays. When you go to space, the astronauts have particular shielding to protect them from gamma rays, bursts, radiations, and so on. That's the electromagnetic spectrum. On one hand, you have nanometer, which is 10 to the power minus 9 meters of wavelength, and the other side, you have the energy shown over here in electron volts. The idea that you have color is essentially if there is an electron sitting somewhere, vibrating in its thermal motion, if it can absorb visible light, it can go to an X-ray, excited state, and the amount of energy that it absorbs will create complementary color. So that's the idea. Now for diamond, this is essentially, a diamond looks like a pure diamond. It's full of carbon atoms. No other atoms are there. That would essentially be a colorless. These are, by the way, lab-grown diamonds by General Electric Corporation. They've grown 3 different kinds of diamonds. Let me walk you through what they are. This is essentially showing a carbon atom. Now, if you add a tiny amount of impurities, like nitrogen, boron is followed by carbon, is followed by nitrogen. Boron has 5 electrons, carbon has 6 electrons, nitrogen has 7 electrons. So if you have more electrons, then you have a yellowish color. If you have less number of electrons, boron, then you have bluish color. That's at least a take-home message. If you have carbon with some amount of boron, you have some color. And those colors will be essentially bluish. Nitrogen will create yellowish. In nature, there's always boron and nitrogen present in the diamond, and that creates some amount of color. Now, if you want to go into a bit more detail, let me walk you through that. Typically, diamond is a covalently bonded insulator, which means it does not conduct electricity. What you see over here in this particular figure is energy and the number of electrons. This is valence band. That means when you have all the bonding, the electrons are essentially confined in this valence band. Let's say if this conduction band and the valence band overlap, it will be a metal. It will be a metallic stuff. It will conduct electricity, it will conduct heat. But this particular substance is an insulator. It does not conduct electricity, it does not conduct heat or so. There's a big gap. That means if you have to really excite an electron from here to there, a whopping 5.4 electron volt of energy is required. It's going to be totally damaging to the diamond structure if you apply that much amount of energy. And it will not be colored. You will not be able to see that. So the issue is, how do you create energy bands such that it can interact with the visible light? That's what creates color. As the young lady asked, how will you distinguish between the blue color of diamond and other gems? Well, first let's understand what creates the color, and then you can talk about how we can distinguish that. So this is a valence band. Now, if you add nitrogen, which has an extra electron, you will have an energy level somewhere in the band gap. So basically, now an extra electron will not need the point of electron. You have a band, and the tail of the band, the high energy level will be pretty high, and the gap will be only 2.2 electron volt. 2.2 electron volt will be somewhere close to the blue, so you have to solve the blue, and essentially the complementary color would show up as kind of a brownish or yellowish. That's how the nitrogen creates color in diamond. Yellowish diamond. Okay, thank you. I'm sorry? Yeah, I got it. Thank you. And if you add a boron, which has 5 electrons, so basically what you're doing is you're reducing the number of electrons. So you're essentially creating an acceptor which is very close to the valence band of the diamond. Now this energy band is of the order of 0.4. So it's very low energy. It absorbs something on the order of red. That's low energy, and it essentially creates boron, a little bit of boron can create a blue color, can create yellow colors. That's how diamond gets its color. And that is sometimes slowed down because you need a colorless diamond, but really large blue diamond. That is an enigma. How much of boron was there in that diamond? How did it even get there? Okay? The other aspect, in the beginning of the talk, I showed that there is this red glow in this diamond which is used, which was generated by bombarding the diamond with UV rays. What happens when you bombard the diamond with the UV rays? A phenomenon called phosphorescence. And the phosphorescence is essentially a time-dependent excitation of the electrons to a higher level, and then it gradually decays over time. So what was found for this, for the whole diamond, there are two peaks. One is a 500 nanometer, which is roughly greenish color, and the one was around 600 nanometer, which is red color. And it glows red, the green becomes kind of orange-yellow. As the green decays, the red essentially decays for a much longer time, and it glows red for a while. Okay? This is observed for hope, and of course, you can tell that it had both nitrogen and boron, primarily boron. But this also gives us an idea that if the phosphorescence of, let's say, the French blue, a hypothetical person, then this would have been a characteristic signal of that diamond. If you would have done for French blue and for the whole, then you would be able to tell the origin of the diamonds are linked because they will have same spectroscopic signatures. Similarly, this particular method can be used to track a diamond if it gets stolen, recut, or something like that. So these are fingerprinting techniques that can be used routinely to identify natural diamonds, because they will have some combination of boron and nitrogen, and each diamond will be very distinct. So this will be that fingerprinting mechanism that can be used to find out which diamond is which. Take a pause. That was essentially the physics and chemistry of the diamond. Still don't know, or I haven't talked to you, I'm sure you know, I haven't talked to you anything about the geology of the diamonds. How do they form? How do they come about? And so on and so forth. We thank you for this. Human story of the diamond's origin in coal mines in India, then Golconda, and then it essentially went through all the way in France, London, back and forth across the Atlantic, and ending in Smithsonian. That's the story of the whole diamond, the famous large blue diamond. Then we also kind of saw what diamond is. It's essentially a carbon, solid phase of carbon. And then, what creates its hardness, what creates its color, the substitution of boron and nitrogen and so on. But now, let's do a little bit of primer on geology and the origin of diamonds. That will be the last, big section. So this shows a map of your overall Earth. And from your day-to-day exposure, no, I'm fine. Thank you. From our day-to-day, known to be the Earth is broken down into several plates. And these are all the plates that are shown. India is somewhere over here. This is the Indian plate. It's getting pushed against the Europe, the Asian plate, and that's where the Himalayas are formed. And this is Tibet. Very high mountains and plateaus are formed over here. Similarly, this is the Pacific plate, and this is the North American plate, and so on and so forth. Divided into plates. Okay. And how did we know that? This theory came about. This is called the plate tectonics theory. Tectonics is a word which essentially describes mountain building processes. This theory came about with gradual observations over the in the 20th century. So the theory kind of solidified after World War. It was noticed before the war. I mean, in the early days, there was an atmospheric science person named from Germany. He found and things for many other countries like Syria, India, and matching coastlines. Not exactly the coastline, but the context of boom, and he was ridiculed, and the idea of continental drifting was kind of shut down immediately, thinking that the continents are really large masses and it cannot move. Now, during the World War, in the Atlantic and also the area needs to be conserved. Okay? And one would think, okay, why does the oceanic plate subduct under the continental plate? Oceanic crust is often denser, it's of the order of 3 grams per centimeter cube, whereas the oceanic, the continental density, crustal density is of the order of 2.75 grams per centimeter cube. So basically, you have a denser material that sinks underneath a lighter material. That's what happens. If that be the case, why does one ocean plate subduct underneath another ocean plate? But the answer is, some ocean plates are more dense than the other, and the density is controlled by the temperature. The newer the oceanic crust, the temperature is higher, they're young and buoyant, temperature high meaning there will become an expansion, and if you are very old and cold, it will be more, that will subduct underneath the younger one. That's the, you have this divergence and convergence, have some sort of non-convergent and transform faults and so on. Under these economics observation, the reason the seafloor spreading was successfully explained is because also the development in material science that solid materials do flow over geological timescales. Rock do flow over geological timescales. It's not that it's molten on the top, the plates are floating. It's essentially solid material which flows over time, which is a special term for that is rheology. That means essentially it's a plastic flow because the temperature are high, material essentially diffuses or essentially undergoes some sort of a dislocation creep, which essentially flows. This is the idea of mantle convection. Okay? So that's the basic background. Of course, the earth is divided into upper mantle, lower mantle. The mantle is essentially the word comes from the German word. It's essentially you have a fireplace, which is the core, the kernel. On top of the fireplace, in the early days, you have mantle. The spelling in German would be M-N-T-E-L. But of course, that has been taken over, and that's the same word we're using. The core is opposed to heart, and over there's a mantle, and the crust is essentially the top portion of the earth. So that's a general geology. The reason I did that is because I wanted to show you this cross section, and I also wanted to show you carbon has many other polymorphs. The two most important polymorphs are diamond. I talked about that. Of course, we are interested in the gem variety of diamond, but there's a very common variety of carbon. That's graphite. Very likely, all of you are typing these days in computers, not looking at much of pencil, but nowadays at least we'll be using pencil and graphite. The pencil leads are made up of graphite. And the graphite is the most stable form in the Earth's surface. Diamond is the more denser, more compact structure in the Earth's interior. So this is a graph showing the pressure in kilobars, and this is the depth shown right here in kilometer. Temperature over here, and this red line shows the diamond stability. That means any conditions of pressure temperature, the diamond will be stable. And over here, graphite will be stable. No, the diamond is not stable at a certain condition, but we still have diamond. It's because of chemical kinetics. Kinetics prevents the diamond to automatically decay into graphite. You need to supply a little bit of heat, and then the diamond is no longer stable to become graphite. That's the thing that we always worry about in our experiments when we're doing high temperature experiments. Also shown over here are these green lines, which are essentially how the temperature within the Earth changes. What you will note is that this is subduction zone temperature. Subduction means when the plates are essentially becoming where it's sinking below, it's a cold plate sinking. That's why you have the temperature is less as you go down. Temperature is not very high, it's a very steep curve. When you have oceanic geothermal, that means the temperature variation within the oceanic crust, it's essentially very warm, and the continental is relatively colder than ocean. What it means is that when continent, the graphite to diamond transition will happen at around this depth of 100 kilometers. Under ocean, it will happen at around 200 kilometers. So that means under continent, you will be able to find diamond. And that's why this particular graph shows this is the dashed line is the lithosphere. The lithosphere is the top part of the crust and mantle, which is a very cold part. That's what constitutes the plate. Underneath the lithosphere, there's a tiny amount of partial melt, which helps gliding of the lithosphere, which is what constitutes the plate. This is the oceanic crust, this is the continental crust, and note that the blue line is the red line over here. The blue line is essentially the boundary of the graphite and diamond. So over here, graphite is stable, over here, diamond is stable. It's in the lithosphere, so you will not be able to sample it. But underneath the whole continent, you will be able to that's essentially, and that's essentially what we have in the southern part of India. Is a trade complex. It's a very old lithosphere that essentially has taken its time. Okay? So these are the lithosphere diamonds essentially will be blown up by this kind of fast-moving lava called kibboliths, and they'll be stored in this kibbolith pipes. But there are deep diamonds that can originate from upper mantle or the mantle transition zone. These are essentially a zone where mineralogical transformations happen, and you can also have lower mantle, very, very deep diamonds, deeper than 600 or 700 kilometers deep. How do we know that? This is how the mineralogy of the rock types that are there in the mantle changes. You have a dominantly olivine rock, then it transforms to porcelain and ringwork. So if you have a diamond with an encapsulation of these dense phases of olivine, you will be able to tell that this diamond has a very deep origin. And in fact, these super deep diamonds, which have origin very, very deep into the earth, oftentimes shows inclusion of porcelain, which means it must have originated anywhere from 400 to 600 kilometers deep, because that inclusion is giving you clues to the original depth of the diamond. And not only that, my own research interest is essentially looking into how much of ocean worth of water is stored inside the Earth's interior. And this water is not a free-flowing liquid water, it is essentially stored within minerals. And the porcelain is a repository of water, and diamonds provided that final clue. Experimentally, we knew that water can be sequestered within the mineral grains, but diamond and inclusion provided that final clue that indeed planetary interior could have a lot of water. Whether it is true for the entire mantle or just a simple sample capsule, that's still a debatable kind of question, but diamond provides those vital clues. The other question is, okay, boron can create blue color in the diamond, and nitrogen can create the yellow color in the diamond. How do you get boron into the carbon? And the diamonds originate in the deep earth, and the borons are found in seawater. Well, you have seawater over here that interacts with the lithosphere, and the lithosphere is made up of crust, and also the mantle is made up of olivine. What happens when you have a plate that bends? It generates cracks, the water percolates down, there's a hydrothermal circulation, you create serpentine, all the seawater, whatever boron it had, gets incorporated into this hydrospace, and they are transported deep down. So that's the process of the deep earth. These are the kind of chemical pipes where you might go deep down and then essentially using shaft you will be able to get the diamonds. This is again a historic map of India. This is Hyderabad, and this is where the Krishna River is there, and these are the places where you have Vajrapur and other kind of chemologic pipes which might have the diamonds. And now there are some resurgence of interest. GSI is essentially exploring these places, and then also private companies which are looking into this diamond explorations. Diamonds are best friend. What is the environmental impact? In the earlier part, when we were discussing about what kind of talk I would give, it's mentioned that I should talk about environment. Diamonds do have a lot of environmental impact. Imagine you're trying to find a tiny gem in a vast amount of rock. You do a lot of excavation to get a little bit of gem. So it will have a humongous footprint on the environment. That is essentially a reef particle that summarizes the finding. This came out in one of the Nature articles known as Humanities and Social Science Communication with Asian authors, the environmental impacts and sustainable pathways of the global diamond industry. GHG emissions are the greenhouse gas emissions. Any kind of operation, mining operation or other kind of operations will release this kind of greenhouse gas, dredging and excavation and so on. Diamond industry tops this particular thing compared to any other gold or any other kind of precious metal. Diamond again has a lot of mine waste, because you can imagine you are essentially wasting a lot of rock to get a tiny amount of gem. So all the indicators, the water usage, mine waste, and the greenhouse gas emission, diamond is the leader. That means it has, to get a little, you have a lot of environmental impact. Okay? So yeah, I mean, as I mentioned, diamond is so nice, it's the best trend, but the depiction of diamond is all mixed. This is a movie from 1960s or so, Pink Panther. It's about Jewel Thief, the pink diamond. This is, of course, something that we are all familiar with. I hope your brother Deshay and This is Blood Diamond. These are all political movies of the implication of the diamond industry and how it impacts human lives in perhaps negative ways. So environmental impact is definitely there in addition to it. What is the way out? Well, diamonds are fascinating, but a lot of research has been done to create diamonds in lab. One way, of course, since diamond is stable at high pressure, you can do high pressure experiments by taking graphite and squeeze it to form diamonds. But that will be a very tiny amount, and it will not be a gem quality that will be used either for industry and for gem industry. The other aspect is something known as chemical vapor deposition. You have a plasma, and essentially you take a diamond seed and you grow diamond by essentially passing methane gas and hydrogen gas, and then the diamond will gradually grow. The technological advancement that is happening is essentially how fast this diamond will grow. And this is, of course, an article from 2005. This was the size of the diamond that grew. There's no nitrogen dope that creates this yellow color. This is just an artifact of the process. This large diamonds can then be used in this kind of diamond anode cell, which is something that I use in my lab. There are two opposing diamonds, very hard. They have a gasket, it weighs the material, and then you can squeeze it to very high pressures, and essentially you can probe what's going on to the materials at extreme conditions within the Earth's interior or any other planet's interior. So both ecological implications and also the gem industry implications. So lab-grown diamonds will have significantly lower contribution to the environment. It's better or more sustainable than the diamond industry as such. I think with that I will stop. I think hopefully through all the interruptions we are able to appreciate the diamonds are fascinating. The beauty and rarity have captivated humanity for centuries. Rich human history, precious gems are deeply interwoven with cultural, historical, and economic developments throughout human history. They provide insights into the Earth's interior, valuable clues about the deeper processes and geological history. Environmental considerations need to be taken into account, significant environmental impacts, and of course it raises concerns about the sustainability of the diamond industry and its process. And of course, lab-grown diamonds provide us with an alternate, and we need to make it better and more sustainable. And this is again Hope Diamond. I had the opportunity of visiting and taking my own picture. With that, I will stop take questions if you have any. Thank you.
Precious and fascinating. দুটো টার্মস যেরকম ডায়মন্ডের সাথে যায়, ঠিক সেরকমই নেচারের সাথে। আমরা খুব মধ্যে আমি শুনেছিলাম আমার সাবজেক্ট বলে, কিন্তু যাদের সাবজেক্ট নয় তারাও মনে হয় এর মধ্যে থেকে বেশ কিছু স্লাইড, বেশ কিছু টপিকস, বেশ কিছু ইনফরমেশন তাদেরও নিশ্চয়ই খুব ভালো লেগে থাকবে ডেফিনেটলি। তো কিছু কোশ্চেন নিশ্চয়ই তাদেরও আছে অলরেডি। আমাদের ফ্যাকাল্টিস এবং স্টুডেন্ট দুদিক থেকে হাত উঠেছে, তার মানে আমার কথা কতটা সত্যি এটা অলরেডি প্রুভ। বাট ফার্স্ট চান্স কে পাবে? স্টুডেন্ট নেবি প্রথম চান্স?
আচ্ছা এসে গেছে।
আচ্ছা ওকে ওকে।
Thank you very much, sir. It's very pleasure listening to you. My two questions are to you. One is you have said lab-grown diamonds. How it has affected natural diamonds? Because I have made one larger report few months back. 26% has decreased the per carat price of natural diamonds and 72% since 2020 in lab-grown. So what is the future of lab-grown and natural diamonds, and how you can relate natural diamonds with lab-grown?
Okay, let me understand the question. So one is you are saying that the amount of production of both lab-grown or amount of cost?
No. The per carat cost has reduced drastically since 2020. It is 26% for natural diamonds and 74% for lab-grown. So why is it so? And what is the future for lab-grown diamonds and as well as lab-grown?
Great question. of the lab-grown diamond, I think the future is pretty strong. Not in terms of, I cannot comment on the gem industry, carpets in a different way. But I can comment on the many technological areas where diamonds are essential because they are very hard. Diamonds themselves are used for abrasive materials, other materials. So the lowering of the cost and essentially techniques to make more lab-grown diamonds are always welcome. And there's lots of endeavor to make them larger and defect-free and going after simple properties. So it will be very good for the industrial applications. There is definitely a future. Whether it is able to make inroads into the gem industry or not, that depends on the human psyche of whether we still follow the natural diamonds are better. But if it fits the pocket, that might actually be beneficial. So I don't know the economics aspect of it. Those are essentially what I read, same perhaps as you. But that's all I can say about it. There's a good future for the lab grown, at least from the technological perspective. Thank you.
কাছে গিয়া মুখের কাছে দাও মুখের কাছে
As we know, humanites are primarily related to the human settings. Can we also find humanites in pragmatic or pragmatic settings? For example, like each specific price.
Okay, that's a great question. So, can we find it in modern? So, most cretons, the reason we call cretons as cretons is roughly they are older than 500 million years, 600 million years. They're very old and stable. They're not essentially participating directly in the studies, not participating directly in subduction. So, they've been there for a really long time. So, typically they are old, 2.5 million years, 1.5 million years or so. So that's where Himalayites have happened in the past. When the Earth was probably much hotter with this really rapid crushing of magnets. Earth has cooled down. This is something called secular cooling of the Earth. So Himalayites, modern Himalayites are rare. All the Himalayites that we know of are very, very old, and that's where many of the diamonds are found. So does that answer your question? So modern settings, the answer is Himalite requires extra bit of a heat in the geothermal profile, and that's called super adiabatic profile. That's the kind of conditions that's required to have this blue. I wouldn't say that's not possible, but observation is against it. It is oftentimes constrained with a really old breakdowns where. So the question is, can we find diamonds in basalt or any other kind of rocks? Well, if you can provide with a source of carbon fluid and or carbonate, so either diamonds can be formed by oxidation of, let's say, methane gas or any kind of reduced gas. The carbon is in a reduced form because the hydrogen is +1, the carbon is -4. So if you can oxidize that, you can form diamonds by making it neutral. Or you can reduce carbonate because carbonate is CO3, so carbonate is over there plus 3 is -2. So what will that oxidation say? +4, I think. So if you can reduce that to C0, then you can form that. These are the two mechanisms you do. So that's what diamond is, right? So either way you can do that, and if that is achieved in basalt, you might be able to get it. Typically it is concentrated more into the deep sometimes so any that's the lab grown diamond. You start with a seed of diamond or some substrate, and then you essentially pass a methane gas, and then you essentially oxidize the carbon to form the neutral carbon. It essentially gets deposited on that seed, and then it grows. And after that, we do the same polishing, same facets polishing to get the really inspired diamond. I have 2 videos, but I'm way out of time, so I don't want to show those videos today, and I don't know whether to. Yes, of course. If I can go back, that's. Yes, this is the one.
Yes, sir. That will be great, sir. We can
I'm
upload
very
it.
happy to see it. Yeah, everything is published and none of it is mine.
Okay.
Any question?
Yeah.
একটু আগে যা, হ্যাঁ।
Sir, you explained how blue diamond is formed by boron due to the boron is in the seawater, but how nitrogen, how trapped in the diamond in
Again, I was just giving this explanation for boron because blue diamond is of course very rare, very, very rare diamond. Yellow diamonds are more common, and nitrogen there are many sources. For instance, sediments is an organic matter, which is essentially CO2 or something those nitrogen can be ammonia gases, ammonia through these processes of essentially fluids, mixing with the fluids and then essentially crystallizing with the diamond. And since they have very similar electronic configuration, they can fit in, but of course it creates this kind of electron issues which essentially show up as well. And it's not that you either have nitrogen or boron, you can have both. And depending on the percentage of both, you will have slightly different pH of color. That's what I was trying to show in the
Any other question?
sure.
whether I distributed the answer or I tried to give the answer.
No, sir, I got my answer. The thing is, it's far on the northern side, like northwestern side. The rift is going there. It's nowhere near South Africa.
Yeah.
So,
yeah.
yes.
The issue that I was trying to highlight is that most of the diamond deposits, I have it in my laptop, but I'm not using it, are mostly located in cratonic parts of the wall. That means it will be within the continents, very old, stable places where there has been some amount of volcanic activity. And of course, after the volcanic activity, you have this diamond-rich places, not diamond-rich, but diamonds will be there. And then, if there are weather, that means through actions of wind, water, then they'll be carried along river streams, and they'll be deposited with conglomerate because the large rocks have same mass as that of tiny diamonds because they are very dense. And then they get deposited in this kind of alluvial, clay bed, or conglomerate. And that's what this Krishna basin was. Essentially, if life was somewhere else, it was then carried through this river, and that's where people were mining these diamonds because you can easily find those. But again, it was well within the continental core, which has been stable for long periods of time.
Okay, so not around the junction of the plates, like within the core of the plates.
No, it's a core of the plate.
Core of the plate,
And
yes.
core of the plates, which means they are very old. The reason we are saying in core of the plate is typically it will be older than the Paleozoic, means 500 years old or so. It will be millions of years old. Stable parts which are not participating in subduction or something like that. They are essentially there in a passive way. That's where most of the diamonds are located.
Thank you so much, sir.
Any other question? Otherwise, আমরা একদম লাস্ট পার্টে দাঁড়িয়েছি অনুষ্ঠানে। ওকে, সো একদম শেষে গিয়ে যেটা বলতেই হয়, ভোট অফ থ্যাঙ্কস, সেই জন্য আমি রিকোয়েস্ট করবো রোশনি দিলে আমাদের ফেস্টিভ্যাল রোশনিটা ম্যাডাম রোশনি সেন। কিন্তু তার আগে রোশনিকে এত থ্যাঙ্কস আমি একটা থ্যাঙ্কস ওয়েদারকে দেবো। আমরা যখন শুরু করেছিলাম পুরো বৃষ্টি ছিল, যার ফলে আমাদের প্ল্যান একটু শিফট করে গেছিলো, প্ল্যান্টেশনটা হয়নি, যেটা অলরেডি আমাদের তো কলেজে সবে সবে জন্মদিন গেছে আমরা জানি, তো সেই উপলক্ষেই ছিল এই প্রয়াসটা। তো সেইটা এইবার আমরা করবো, কারণ অবভিয়াসলি আমাদের মধ্যে অনেক গেস্ট প্রেজেন্ট করেছে, সুতরাং এত ভালো অপরচুনিটি আমরা মিস করবো না। So, Roshni, and then.
I have the honor to read the formal vote of thanks. Thank you, Dr. Mainak Mookherjee, for this enlightening journey you have taken us and enlightened us with the historical and also geological knowledge of the untold story of the diamond. I also take this opportunity to thank our officer in charge, Dr. Sister. She's not here right now, for her encouragement for organizing this program. I also thank our IPS coordinator, Dr. Jayanta Vishwash, for giving us the support to organize the program. Special thanks to the head of the Department of Geology and the two geologic colleagues for giving us this opportunity to have this wonderful presentation today. Thank you, Nibedita and Professor Ghosh. I also thank all my respected colleagues who are here patiently hearing this. I also thank the non-teaching staff of the college for helping us to organize this program. And last but not the least, you have been a wonderful audience, dear students, and you have also asked insightful questions. Thank you, everybody. And we also hope to hear from you in the future. We will be very glad if you can share your PowerPoint presentation with the students. Thank you very much, sir. Thank you. Now we can proceed for the plantation, I think. Shamragi, will you please guide us? Achha, just 1 minute, we'll have a group photograph with the speaker. Students and teachers, can you please come?
সামাল দিলাম স্যার সরি
No worries. আমি
হচ্ছিল তো লাইভ
আমাদের সাউন্ড সিস্টেমে লাইভ বোঝা গেছে।
কি করতে যাচ্ছি বলে দে শুনতে পাবো তার লোকজন
সিস্টার নিবেদিতার নামাঙ্কিত এই যে আমাদের গভর্নমেন্ট কলেজটি এর 10 বছর পূর্তি উপলক্ষে আমরা একটা প্রতীকী বৃক্ষরোপণ করতে চাইছি। আজকে যে গাছটা আমরা লাগাবো সেটার নাম হচ্ছে নীলচূড়া বাংলায় বলে, আর তার বিজ্ঞানসম্মত নাম রাস্তার ধারে ধারে প্রচুর আরো বর্ধিত করতে হয়তো আমাদের কলেজের মাঝখানে একটা নীল আমাদের
কমেন্ট্রি করতে কমেন্ট্রি করতে
আমাদের আজকে সম্মাননীয় অতিথি ডক্টর মৈনাক মুখার্জি এসেছেন। নেচার ক্লাবের সদস্য আমাদের স্টুডেন্টরা সবাই স্যারকে সহযোগিতা করে এবং আমরা সবাই গাছটি এখানে রোপণ করি। এই গাছটা আমরা বলি ব্লু জ্যাকারান্ডা। আর এখানে একটা অদ্ভুত কোইন্সিডেন্স হয়েছে, ব্লু ডায়মন্ড নিয়ে কথা হবে আমি জানতাম না, এর নাম হচ্ছে নীলচূড়া বাংলায়, ব্লু জ্যাকারান্ডা। এই বৃক্ষটি রোপণ করে আমরা সিস্টার নিবেদিতার নামে নামাঙ্কিত আমাদের যে গভর্নমেন্ট কলেজ তার 10 বছর পূর্তিকে উদযাপন করব। স্যার প্লিজ ম্যাডাম স্টুডেন্টরা এসো, তোমরা এসো। মাটির তালটা লিফট করে স্যার ম্যামের হাতে দাও, ওখান থেকে তালটা লিফট করে স্যার ম্যামের হাতে দাও। তাহলে
ফোনটা কেউ রাখবে?
এই এটা ধর আমি গাছের মাটির গোটা মাটির ধরতে লাইভ ধরতে গাছের গোড়ায় মাটি দিতে হবে
আচ্ছা আমরা একটু সিকিউর করে দিই এটাকে। এখানে এসে এটা মার্ক করা যায় কেমন? একটা করে তোলো, একটা করে তোলো, পরিষ্কার থেকে ওই সাইড থেকে তোলো, ওই পাশ থেকে পাশে আসলে হ্যাঁ আচ্ছা, গুরু দায়িত্বটা নিচ্ছেন আমাদের নেচার অবজারভেশন ক্লাবের মেয়েরা। আমরা এই গাছটাকে ঘিরে দেব যাতে আমরা আরো ভালোভাবে ডিমার্কেটেড ভাবে যত্ন নিতে পারি। গাছটা খুবই স্পেশাল গাছ, যেহেতু 10 বছরটা কমপ্লিট করছে আমাদের কলেজে।
আর মেয়েরা এই ব্যাপারে একটু এগিয়ে আসবে, হ্যাঁ, মানে গাছটা কেমন আছে দেখবে, তখন আপনাকে ম্যাডামকে ডাকবে, ডেকে গাছটার পরিচর্যা করবে।
এসো মেয়েরা এসো, হাতে হাতে চলো চলো যাই।
হুম